Hello everyone, it's Coder from 19. Today's day 98 in my challenge day. And in the last video, I tried to apply the material property on the obj model. But when I look in the code in the GLSL, I just didn't understand. I didn't fully understand about the specular reflection in terms of energy conservation on the surface. So today, I'm going to learn about the Phong BRDF again by reviewing with the course that I mentioned before. So today's learning material looks like this. You can search these two in computer graphics course. This video uploaded by the 2 minutes paper. Okay, let's start.
Look like? Well, first, on the left side I see I. This is intensity. Well, what is this? Well, no one knows, because we have not radiance, not something very physical here. This is going to be a simplified version of the whole rendering equation, basically a bunch of hacks, if you will. Something that is vastly simplified. It doesn't really have a physical meaning, it doesn't have physical units, but it works, it's beautiful, and it's a good way to understand what's going on. So the intensity that we measure is going to be the product of an ambient coefficient of an object. This is dependent of the object. This means that this means something like the color of the object. And the I is going to be the intensity, the ambient intensity of a scene or the light source. And later on we're going to be talking about why this is interesting. So this is an example. We have a blue object over here, and it's the same color everywhere. Why? Because the formula doesn't depend on anything. There's just one coefficient that's multiplied by this intensity of the scene. So that's an ambient shading. What else is there? There's the diffuse BRDF. This is what we compute is a diffuse coefficient. What is the diffuse color, the diffuse albedo of this thing? And there's going to be a product of L and M. This is what we did before. Diffuse objects look like that. Please raise your hand if you have ever done any kind of diffuse Lambertian model in graphics. Okay, excellent, great. And just another thing, this diffuse coefficient is the very least RGB. Okay, so this is how much light is not absorbed on every different wavelength, because I cannot describe colors in one number. At the very least RGB or a continuous spectrum, just for the record. And now it's looking better because I can more or less see where the light source is for this diffuse shading. There's also a specular BRDF. What I compute is V dot R times the specular coefficient, and V is the vector pointing towards the viewer, and R is the reflector. There's going to be examples of that. Okay, so just that you see the formula here. And there's an N, which is a shininess.
So just for quick notes, when you do a dot product of two vectors, which is in this case a u and v, it is equal to the size, uh, the magnitude of u, and multiply with the magnitude of v, and multiply with the cosine theta. Cosine theta, this theta means the angle between these two vectors. So in this case, so if the magnitude of these two vectors is equal to 1, which is a normalized case, the dot product of result is just equal to the cosine theta.
Factor. In the next assignment, you will play with this yourself. So for now, I will keep this a secret, what this exactly does. And whoops, I'm going to jump through this because I would like to ask a question later on, and you're going to find out the solution. Excuse me. Later on, I'm going to jump through. It's a secret, what this exactly does. And whoops, I'm going to jump through this because I would like to ask a question later on, and you're going to find out. The solution, excuse me. So this is how the specular highlights look. And if I add up all of these things, ambient and diffuse and specular, I get some complex looking model that looks something that approximates physical reality. So I just simply add all these terms up. Okay, well, I have something like this here, and I have on purpose removed the light source from this image. But probably everyone can tell where the light source is expected to be, right? So raise your hand if you know where the light source should be. Okay, cool. Where should it be?
Above of the
Exactly.
walls and
Exactly. So it's going to be above the spheres, and this is exactly where it is. So these material models are descriptive in a way that I get images that have some physical meaning, that resemble physical reality. Well, let's take a look at an actual example. The question is, what would this region look like, the one that I marked, like this pixel, if pixels existed in the real world? would it look the same if I moved my head in reality? And that sounds like a, you know, it sounds like a tricky question. Yeah, I've seen the answer, yes. Let's say that this part is purely diffuse. I don't see many specular reflections in there. Diffuse is L dot n, so light vector direction times the normal. Does it change if I move my head? Well, how to answer? This question, you don't only need to see what is in an equation, you have to be aware of what is not in there. Does it change if I move my head? Raise your hand if you know the answer. It's very apparent to many of you. Yes?
Should I answer?
Yes.
It does not change if I move a little.
Okay.
But it might change because the specularity might move over there.
Yes, that's very true. So it doesn't change because we know that it doesn't change. I mean, the walls look the same if I move around. I mean, I'm not talking about shapes, I'm talking about colors. They don't change. A mirror, however, does change. And the mathematical reason for this is that the view direction is not in this equation. I can change the view direction all I want, and nothing will change in the diffuse BRDF. So this is like a general mathematical trick or principle that you can use in a number of different things. Don't just look at what variables are in there. Try to think of variables what you would imagine that would be there, and okay, why are they missing? And that's also information, not what's there, not only what's there, but what is missing is valuable information. So what about these regions? These are specular highlights. These are described by the specular BRDF V dot R, so viewing direction times the reflected light direction. And let's actually compute what's going on. So I would be interested in the intensity, this fake something of this point, where this is the light vector, this is where it points to. It is probably reflected somewhere there because it comes in and it's an ideal reflection, so it's going to be reflected in this direction. And this is where I am, just for example. So I'm interested in V dot R. This is going to be a cosine. There is a small angle between V and R. So if there's a small angle, that's cosine of a small number, that's large, that's close to 1. And there's going to be a huge scalar product, therefore this point is bright, and this is indeed bright. And the question is, which is very easy to answer in a second, is does it change if I move around? Does it change?
Yes.
Obviously it does change because V is in the equation, and if I change this around, this is something different. For the specular BRDF, this is going to be bright. Just one of my favorite intuitions of this V dot R, because otherwise this is just letters. This means how much am I standing in the way of the light? So, life lesson. If you can't find the water droplets on the floor after having a shower, move your head around, because that's specular. If the windshield of a car is too bright and you just can't take it anymore, move your head around. This connects to the physical reality around us. And that's good tips in case You didn't know that you need to move your head around it. Things are too bright. And now you know. Okay, so this is the point where we can just for a second stop and marvel at how beautiful things we can create with such simple equations. And the rendering equation is going to be even more beautiful than that, like infinitely more beautiful. And there is some additional beauty that you can think about when you look at images like that. Okay, how would I shape this point? Is this diffuse? Is this specular? Why does it look the way it does? So you can, if you have nothing better to do, you can think about these things when on public transport. Let's call this thing the illumination equation. This is the fake, simpler version of the rendering equation. Now, what is in there? Most of this is familiar. There is an ambient shading term, and then there's the diffuse L dot N, there is the specular V dot R. We add all these together, and we multiply this by the amount of incoming light, because if there's no light sources in the scene, there's no light. Light is not coming from anywhere, therefore this is all multiplied by 0. If there's a bright light source, then things get brighter. So we multiply by this incoming light. And what is important to know is that this is only the direct effect of light sources. This sounds a bit esoteric at the moment, but later on, a few lectures down the road, we're going to be all about indirect illumination. And do these like that. And this is neglected, and the ambient term is used to make up for it. You will see examples of this in the next lecture. And this is a crude approximation, but it's still beautiful, it's easy to understand, and it serves as a stepping stone to solve the real rendering equation. But this is not done. One thing is that if there are multiple light sources, the scene is expected to be brighter, so I would compute the whole thing for multiple light sources. So there's going to be a sum in there. And inside the sum, the indexes are the number of light sources, basically. I just didn't want to overcomplicate this. But still, something is still missing. This is not done. I arrive to a point, I compute this specular ambient and diffuse shading, and I am not done. Let's discuss how ray tracing works, and we'll find out. So, the first thing is that what you see here is non-trivial, because What you would imagine is that you start shooting rays from the light source, and then some of the rays would make it to the camera, to your eye, and most of them won't. So we go with a simple optimization that we turn the whole thing around and then we start tracing rays from the camera. Because if I start tracing from there, I can guarantee that I deal with rays that are not wasted, because I'm not interested in the light rays that do not make it to the camera. So if I start from there, I can guarantee that this is not wasted computation. So how do we do this? There is this camera plane. We will discuss how to construct such a thing. And we construct rays through this camera plane. And what I'm interested in is the projection of the 3D world to this plane. This is what you will see on your monitor. So I shoot rays from this camera and I intersect this against objects that are in the scene. I want to know where is the light stopping, what objects does it hit and where does it get reflected. So the second is intersection with seen objects. I have to realize that it hits this sphere. And then I stop there, I compute the basic shading terms like the diffuse and the rest. And then I don't stop there, but I'm interested in where the light is reflected. I need to continue from here. And this light ray may be reflected or refracted. And I need some kind of recursion in order to account for that. And the recursion works in the following way. I stop at this point where I hit the ball, the sphere, and what I do is that I imagine that this is now the starting point of the ray, and I'm shooting the ray outwards, and I start this ray tracing algorithm again. So this is how the recursion works. This was missing from the formula. And this is just what the text version of what I have said for those who are reading this at home. And you will deal with refractions yourself. Now, we have some
Sorry about there's an error in my camera setting. So I'm just going to recap what I learned today and going to finish this recording earlier than previous video. So first, in the MV Pro samples, they applied some energy conservation concepts here. Let me see. Okay, these power of max dot product between V and R vector with the K shinies is exactly same that I learned from the video. But this energy conservation term is slightly different and this is not that I didn't this is not the thing that I learned in the video. So by just ignoring this term, it seems that specular is defined well inside our wavefront GLSL. And also the diffuse header, diffuse function. So max dot normal vector with the light direction. Okay, this is also really good. But you guys may curious about why we use the max clamp function for the dot product result with the 0, 0, because we are not caring about the how can I say this? Let me say that um, when the angle between normal vector and the incoming light direction is more than 90 degrees, cosine 90 degrees is equal to 0. So also if the angle is over the 90 degrees, the cosine result going to the negative at some point. But it is not it doesn't make sense the negative coefficient when we calculate the rendering equation. So about the case under the hemisphere of the hemisphere that can the outgoing direction can go out is the some space some local space that light can go outside. if the dot product result is outside of this hemisphere, we don't care about it. So we set the 0, 0. And we do the same thing for the specular reflection here. Um, Actually, I want to explain this with the notes, but I have no iPad right now, so I'm sorry about that. So by getting back to Phong BRDF, we need an illumination model to simplify the in the reality physical world into our computer programs. So in the simpler illumination model, we use three terms, which is ambient, diffuse, and specular. And there is also some emission of object, but we don't care about it in the illumination model because it is just a constant term in uh, that we just can add when we calculate it. So it is not important. So ambient is not related to physics at all, but it makes a good default appearance. And we do product of ambient coefficient to intensity of ambient. So roughly, this is a default color of a certain object. The equation is represented like below. And the diffuse is also called as albedo in computer graphics. The diffuse and the other coefficient may take different values for different wavelengths. So for example, this blue object can absorb green light, but when it reflects the light, it can reflect all the incoming blue light in the meantime. So it absorbs red color and the green color inside the object, but it reflected the incoming all the blue wavelengths to our eyes, so we can see this object as a blue. And the equation of the diffuse term follow this equation. We just center it, okay, like this. And as you can see in the equation, diffuse term is not related to the viewer's direction because it only depending on the light incoming direction and the normal vector of the object. So even though we moving around our head to around the scene, this intensity is constant uh, against to our viewing direction. But on the other hand, specular term, if you see this equation, it is dependent on the viewer direction and the incoming light direction. So unlike diffuse, specular reflection is dependent on the viewer's direction as it denoted in the equation. And n is the shyness. Also recorded as a roughness in some material editor. So intuitively, this is a power. Let's see. This is an exponent term of this equation. So when the n is close to more than one, this v dot r, the result of v dot r will be how can I say that? Will be so bright in terms of the brightness. But if the n term going to 0, sorry, yeah, I didn't understand this roughness. Yeah, so if the these rough shininess coefficient going to zero, in this case we only have the constant coefficient of these k underscore s, and these object illumination is usually dependent on the diffuse term only, like the surface of the undersurface of this blue object. So the Phong BRDF is basically the combination of these ambient, diffuse, and specular term by dependent on their intensity. The intensity has two parts. So we have one intensity for the ambient color and the other intensity from the direct light source in the scene. And we multiply the diffuse term, we multiply this intensity of the light by the addition of diffuse term and the specular term at once. And this image shows that what is the Phong BRDF result. And the Phong BRDF only accounts for the direct illumination. On the other hand, if we take indirect light on the surface, we can call it as a global illumination, and which is the I interested in to implement in my application in the real-time sense. Also, if there are multiple light sources, we should modify this equation. This equation is not the complete one. This only take care about just a single light source in the scene. But if we have a multiple light sources, we need to add some sigma term for the cases because we need to iterate this intensity of the light dependent on the light position in the scene. So this is all for the Phong BRDF, and the next thing was a ray tracing overview. So we construct in the reality, the lights start from the light sources and it bounce a lot of our scene. The light bounces on the surface infinite time in a certain spaces, but we can't calculate it. We can't compute it in our computer because computer has some limitation of the memory spaces. Also, it has a limitation of a computing power dependent on the CPU and the GPU. So the clever algorithm is to start the ray from our camera, and we shoot the ray from the camera, and we taking care of the intersection on the surfaces in the scene, which is the reverse algorithm. So first, we construct array as origin of camera's position and compute the direction from camera to the current pixel position. So if the world origin is here, the pixel coordinate will point to the here, and the camera position vector will point to here. And we do the subtract these pixel coordinates represented in the world space by this camera's position. We can get this direction of the camera, direction of the ray to the scene. And using the inverse of projection and the viewing matrices, we can convert these ray represented in the projection space into the world space representation. And then we check an intersection with the scene objects like this. This is a missed case, and this is an intersected case with the scene object. And if it is intersected with the object, we do shading on the surface. It means that we determine the color of the object, and we reflect or refract the light directions. So if this was the transmittance transparent object, the light will refract the surface like this direction if it was a glass. But if it is some uh, I forgot the word. Yes, if it is some opaque object, it will reflect the light to the light sources or or the other object in the scene. And we recursively iterate this algorithm following our predefined depths of recursion. For example, like 64 depths of recursion or the 128 depths of recursion. And the details of the scene is depend on these recursion depths because the more we iterated this algorithm the more we iterate this algorithm, the more the scene becomes detailed. Okay, so this is to the end of today's recording, and thanks for watching. See you next video.